Hello student, very good morning to all of you. I think, do you remember what were we discussing yesterday? I think we were discussing about the carbohydrate, basics of carbohydrates we are discussing, and some of the part of that basics of carbohydrate we have learned yesterday. I think how to give the name of the monosaccharides after doing the classification of that carbohydrates. We have discussed nomenclature of the carbohydrates, and as we know that nomenclature means what? The systematic way of giving the name of the organic compound is known as nomenclature. Suppose in carbohydrates, monosaccharides, depending upon, suppose is a common, according to as IUPAC, as we know that there are two systems generally used while naming any organic compound. One is called as a common name system and another one is known as a IUPAC nomenclature system. So according to that, we are generally giving the name of the organic compound. Specifically in this carbohydrate chemistry is totally what we can call it as a different branch, and therefore the nomenclature system according to as IUPAC stand for International Union of Pure and Applied Chemistry. According to this system, the carbohydrates are generally monosaccharides are generally termed as glycose, and we know that OSE is known as a sugar unit. OSE, remember that is the last suffix or the prefix we are using. OSE is termed as a sugar unit present in the carbohydrate. And another thing we have seen there, suppose mainly according to as a definition of the carbohydrate, it is defined as carbohydrates are polyhydroxyaldehyde or ketone is known as carbohydrates, and that according to these definitions, suppose as aldehydes are group present in the carbohydrate, then we can call it as a aldose. Three were taken from the aldehyde. First three letters are taken from the aldehyde, and OSE, that sugar, three words are joined together, and therefore we can call it as a aldose. And there we have seen, suppose as a glucose, we know that everybody knows that it is a common glucose, and that glucose having as a molecular formula C6H12O6. There are 6 carbon atom, and therefore depending upon the number of the carbon atom also we can add there. So there is a aldehyde group present in the glucose, so we can call it as a aldohexose. Hexo means 6 carbon atom indicate, ALD 3 letter indicate aldehyde group, and OSE indicate as a sugar unit. So glucose is one of the sugar. So how that glucose is obtained from, what are the method for the preparation of the glucose, and naturally we know that, but chemically, or what we can call it as a laboratory method, how we can obtain that one, that we will see shortly after talking about something about that after the nomenclature system, how to actually synthesize these compounds. So that we are going to learn there. And now here, as we know that the simplest starting material in a carbohydrate, so it is generally referred as a reference compound, which is known as a glyceraldehyde, and as we know that it is sometimes referred as a diglyceraldehyde, and sometimes there is a plus sign is putting after that. D means that is a experimental that indicate as a optical activity vector, that glyceraldehyde if you see the structure of glyceraldehyde, as we know that, and it has a D configuration. Why it is given as a D configuration, that also I think we have discussed. When OH is on the right hand side, then and then we can call it as a called it as a D. That D and L are the relative configuration of that carbohydrates, and as we know that this glyceraldehyde generally, or the carbohydrates are generally represented on the blackboard, or we can call it in the notebook according to as a Fischer projection formula. And the first rule tells us that the compounds, the carbohydrates are generally written vertically according to as a Fischer projection formula. And that formula also we know that suppose as a from Wedge formula, there are the different traditional ways to represent the organic molecule, one from another. I think 4 conventional ways to represent the organic chemistry, to understand the stereochemistry behind it. And once you know the stereochemistry, you can know their physical properties as well as chemical property, and you require a lot of imaginary power, and this stereochemistry is there. And according to that, in your previous classes you already learned those stereochemistries are there. Wedge formula or flying formula. Second one is a Sawhorse or Newman projection formula, Fischer projection formula, how to interconvert one into another, that everything you know that. But here just yesterday we have seen as a, let us see the general basic carbohydrate, which is used as a reference compound is this one, the OH and hydrogen atom. Here is a CH2OH. This is a reference compound. It is termed as a D plus glyceraldehyde. Glyceraldehyde. This is a common name of this compound, right? This is the common name of this compound carbohydrate. And now the IUPAC name, there is aldehyde group as well as what we can call it as a IUPAC name. So 3-letter aldo. And how many carbon atoms are there? 1, 2, 3 are there, and therefore aldo triose. That is the IUPAC name of this compound. And up to this I think we have seen, as well as we know that this glyceraldehyde has a one chiral center, that is it is shown by asterisk like this. And chiral center means only one chiral center. Definitely this compound is optically active in nature. Optical activity is one of the physical property of the organic compound, and the instrument used to determine, to measure the optical activity of the organic compound is a polarimeter, that we know that. And when the chiral center, according to as a wants of rule, there is a one rule, 2 raised to n number of isomer we are getting, that is a isomer. And as we know that isomer means what? Having molecular formula is the same, but there is a different structures, or that type of the phenomenon is known as isomerism. And that whatever isomers we are getting, that is what. But here specifically this is a D, because that OH, this is the lowest chiral carbon atom, we can call it, is over here, lowest chiral center present over there. With respect to this, the D is relative configuration are assigned to such carbohydrates. And therefore if you put here according to as a 2 raised to n, it is a want of rule. So according to that isomer we are getting, and n indicate as a number of chiral center. Only one chiral center is there. So 2 raised to 1 is equal to 2 isomer. One is if you put as a mirror over here, if you write this one, hydrogen atom comes this side, and hydroxyl group comes on this side, on left hand side, hydrogen goes on the right hand side. This group top, bottom group and the top group, they are remains as it is. These are the two isomers, first and second, both, and these two compound has a special relationship between these two structures. What is that? We know that they are enantiomers. Enantiomer means what? Everything is the same. Physical properties as well as chemical properties of those molecules are same, only they differ in their rotation. One rotating the plane of polarization right hand side, another rotating the plane of polarization to the left hand side. So that is the only difference. Other thing all is the same connectivity of that carbon framework remains is the same, only their rotations are different. So that type of the thing is called as the enantiomer, that also we have seen. And now starting one trick I am now there is a what we can call it as a, you might have heard that Kilone Fischer synthesis, have you heard about? This is one of the major contribution toward that carbohydrates is a Kilone Fischer synthesis, and he synthesized the compound in the laboratory. So Kilone is a scientist name, and Fischer also, as we know that it is also as a scientist name. They are synthesized this compound, that kind of the carbohydrate in the laboratory. How they are formed? Let us see. Begin with here. I am going to give you the trick regarding that Kilone Fischer synthesis, how they synthesize in the laboratory, that we will see later on. But here, how to remember, simplest one, how to get that compounds. So that we are going to learn over here. So what they did, suppose as a starting compound they have taken as a glyceraldehyde, then treated with the hydrogen cyanide, then they got the cyanohydrin as a derivative, and that derivative they further followed by the hydrolysis. That cyanide group is illigate hydrolysis converted into as a acid, and that acid further what we can call it as a there is a increase on the one carbon atom, or we can reduce that carbonyl group into as a what we can call it as acetyl group, and then Rosenman reduction like that, or sodium amalgam specifically they are using over there for the synthesizing that of the Kilone Fischer synthesis we will see later on. But let me tell you here how this glucose is derived or obtained from the starting from the precursor, we can call it as a glyceraldehyde. Now let us see one word I am going to give you over here is a get and Raxel. Get Raxel, you might be knowing the get Raxel, G-A-T, get Raxel, get Raxel, you can Raxel, you can remember. Get Raxel, what this word means. I am trying to explain these things in what we can call it as a get Raxel means how to remember, how to arrive, how to get that glucose. Regarding that, get means here it is a suppose we have a simplest compound, suppose as we know that glyceraldehyde, right? And suppose this is a glyceraldehyde. I am going to give what we can call it as a tree diagram over here. Suppose as this Z, and there are two, suppose what we can call it as a here A, and here you can call it as a T over there, right? The A, E, and sorry, not E, get, not, this is not the gap, there is a gate, I am sorry. So gate means what? Gate. So this is G, here E, and there T is there. And then this further again, as we know that there are the 3 carbon atom over there, so you can call it as a triose, this one, right? Triose. And this, there are 4 carbon atom, so you can call it a 4 carbon atom, so you can call it as a tetrose. This one you can call it as a tetrose. Tetrose, these are the tetrose. And this tetrose further has another one, that this is a gate, G-E-T, gate, then R-A-X-L. Let us see here, R we are writing over here, and here is a, and here also has a 2 types are there. One is called, here is a X, here you can call it as a EL over there, right? And these are the thing we can get over here. And now these are the these 5 carbon atom here, so you can call it as, this one is a pentose, right? Pentose. And here also you can call it as a pentose. And here also as these are the 5 carbon atoms are there. Here 5 carbon atoms are there, and therefore we can call it as a pentose. That is also as a pentose, right? This is also as a pentose. And so in this way we can get, we can lengthen the that carbohydrate or the carbon skeleton by 1. So in this way, with that tree diagram we can remember. And now here also we can increase over here. So you can write, here is a 6 carbon atom, here also as a 6. So there is called as a hexose. Here you can call it as a hexose, and this is also as a hexose. And here also again you make it, these get split into as a 2, so that is also as a 6 hexose. This one is a hexose, this is also as a hexose, right? And here also you are going to get as again is a 2, or there they are also as a 6 and 6 member hexose. Here also as a 6, here like this. So this is also as a hexose, and this is also as a hexose. As we know that they are the IUPAC name hexose, and this is also as a hexose, right? So as we know that glycerol, starting from the glyceraldehyde, we can get this type of the compound further in a more another way, that is this type of the things. Now let us see, this is just as a general tree diagram I have drawn over here. Now let us see how we can achieve the simplest one, what we can call it as a Kilone-Fischer synthesis, which is known for the lengthening of the carbohydrate. So we can extend the length of carbohydrate, or we can increase the carbohydrate by adding 1 carbon hydrogen, so that we will see. But here, as we know that the glyceraldehyde is a structure over here, right? Glyceraldehyde I am writing over here is a glyceraldehyde structure. Everybody knows that CHO, just now we have seen. Here is a OH, then here is a hydrogen atom, now here CH2 and the OH, right? This is a structure of glyceraldehyde. This is a G stand for glyceraldehyde, you can remember. This is a D-glyceraldehyde, D plus glyceraldehyde, glyceraldehyde. This is a structure of glyceraldehyde, and this we can call it, this is a Z, right? And here are 3 carbon atoms are there, and therefore you can call it as a triose, right? This one is a triose, right? This one is a triose. And after that there is a gate, means what? This further is converted into this way. You can draw this is a fourth carbon atom, or there also as a fourth carbon atom we are adding over there one carbon atom, so that you are going to get here how there this E means what? E means erythro. E means what? Erythro, or you can call it as a D erythro. D erythro. Yeah, D erythros. And here T means what? There is a D triose. Last suffix OAC indicate as a sugar unit. You remember there is a D erythro, and they are the tetros, right? These are this is a triose, and they are the tetros. These are the tetros, means 4 carbon atom. Now look at here, how do you get that erythros? What do you mean by erythros? What do you mean by the triose? Remember here erythros means what? Now I am writing this glyceraldehyde. Glyceraldehyde structure is as it is CHO. Then I am writing this one. Then OH, and this CH2OH, right? And I am putting one horizontal line over there. And now here also as the same CHO, what I am trying to explain over here, how we are going to get as a erythro or the triose CH2OH. I am putting this, whatever this OH, that is on the right hand side, and therefore because D erythros means what? Hydroxy group are on the right hand side, and therefore that designated as a D is a relative configuration. Similarly here also the hydroxy group, remember the lowest chiral center you have to consider while assigning D or L configuration. Look at here, the hydroxy group are on the right hand side, and therefore it is designated as a D, whereas here also as a OH on the right hand. Now is a erythro. Now same OH group you can add over there here, and hydrogen atom over here, and this is the structure of erythro. Remember, this is the structure of erythro. In a triose means what I am going to do, in this case the OH group I am put on the left hand side, and this is a hydrogen atom on the right hand side. So this is the structure of D triose. This is a tetros, this is also as a tetros. Why they are termed as a tetros means there are the 4 carbon atom in the straight chain. Here also as a 4 carbon atom, and this is known as a erythro. Erythro means the same group are on the same side of the if you read and in a carbohydrate chemistry, always remember the carbohydrate compounds are always written vertically. So, and most oxidizable compound or the group are keeping at the top, and so this is the structure of erythro and the D triose. And now remember here also, now what is going to happen from this? There is again two things are happening over here. Remember here also as a we are going to get here is a DR means a DR means here is a pentose we are going to get here, pentose, right? Here also we are going to get as a pentose, right? Pentose. And DR means what? Ribose you are going to get over here. D means here, this R means ribose. You are going to get DR ribose. And here A means arabinose. This D arabinose, and these are also as a pentose. And but here how do write that pentose? What is that? X means what? Xylose, D xylose here, D xylose, and here is a D lizose. here is a D-xylose, D-lysose. So these are the, and how they are very easy once you know the trick. So we can synthesize, we can get this compound very easily in the laboratory. Later on we are going to see the how actually the compound are obtained, so that we will see later on. But here just how we are going to arrive from where the glucose we are going to obtain by using as this method that we are going to see. And due to the limitation of this blackboard, I am roughing this above thing. So remember here, so this I am keeping as it is, so that now remember D-ribose I am starting from this one. So D-ribose, right? Here I am writing this one as D. Here I am writing D-ribose over here. D-ribose. D-ribose means this one. How do I get this compound? Look at here, right? CHO I am writing as it is. Now I am trying to draw the structure of D-ribose, and now here is a CH2OH. Now look at here, 1 2 3 4, and you have to keep this as it is. 1 and 2 they are as it is, right? This OH on the right hand side, OH on the right hand side, hydrogen and hydrogen atom they are on the left hand side. I am going to insert one hydroxyl group here. I am writing over there, right? I am putting this as a empty now. Now moving toward as a D-arabinose here. D-arabinose. D-arabinose, what I am going to draw over here is a same thing. Then CHO I am going to put on at the top, then CH2OH, and then this one. Look at this one here, this 2 hydroxy group I am this OH on the right hand side, whereas in the second hydroxyl group on the left hand side, and put that hydrogen atom, and this is a empty as it is, right? Okay, you understood up till now. Now what I am going to do over here, D-ribose, structure of D-ribose. Now this hydroxy group OH, because the after the cyanohydride, hydroxyl group is going to get on either this side or that side, but here you remember OH you put on the right hand side and hydrogen on the left hand side. This is the structure of D-ribose. And whereas arabinose, structure of arabinose, now what you have to do here, in the first case we have put the hydroxy group on the right hand side. Now you have to put the hydroxy group exactly opposite to that on a left hand side and hydrogen atom on the right hand side, and this is nothing but the structure of arabinose. Understood this one? And now let us look at the another one. Again these are going to convert into further 2 because we know that number of, look at here, 1 2 3 chiral centers are there. Can you tell me how many isomer do you get over there? 2 raised to 3 means 2 raised to 3 means what? 2 into 2 into 2. Total you are going to get as a 8 isomers are there, and therefore now look at over here how we are going to get a total are 8. So here D-arabinose, these 2, and we have D-arabinose, and another is left. We have X and Z. We have here 8 because we are going to get as a 8. So here 2, and here again as a 2. And now here what is that? what I think we have rubbed out over here. So here that is a xylose, D-xylose, and here we are going to get as a D-lysose, right? Lysose. Now here again you have to remember here, as far as this is concerned over here. So I think we have missed something over here. The had D-erythrose and D-threose from the D-arabinose. Here we have only, just remember here we have drawn letter C over here. Here actually it is obtained from the D-arabinose obtained from the erythrose. So there is a CH2OH. Remember that erythrose, OH and OH, H and H. And now I am putting the hydroxy group on the left hand side. So that is the structure of arabinose. That the correction you have to make over there. Now from this we are going to get as a D-xylose and the D, because this we have obtained from the D-erythrose, and we know that the D-erythrose, the structure, the CHO, then this CH2OH, OH, OH, H and H, because we have got these two structure, ribose as well as arabinose, because these hydroxy group, they are same. And why they are termed as a D? Remember here also as a this, and this is from arabinose. Now is the threose. This we are getting from the threose, D-threose, right? The D-threose. We are going to get this xylose and this lysose from the threose, and we know that the structure of threose is this one. Let me draw here CH2, then here 2 CH2OH, because this is a triose, OH here, H and HO, and hydrogen atom over there. From that we are going to get as a xylose, and from there is a D-lysose. And now xylose, look at here CHO, here also as a CHO, then we are going to CH2OH. Here also we are going to write CH2 and the OH, right? Now look at here the structure of threose. You write down as it is OH, HO, H and H. One empty put here, 1 and 2. This OH and H over there, then HO and H over there. Now when that xylose, you have to put the hydroxy group on the right hand side, and whereas hydrogen on a left hand side. Similarly here, exactly do the opposite thing over here. Hydroxy on the left hand side and hydrogen on the right hand side. So this is the structure of xylose and this is the structure of lysose. And now again there are three chiral center, 2⁻³ means 2 into 2 into 2, total number of 8 isomer you are going to get. Here is a 1, 2, then 3, 4, then here will be the 5, 6 and then 7 and 8. These are the structure you are going to get over here. And now this as we know that 1, 2, 3, 4, 5, these are the pentose. Now what you are going to get here? Here you are going to get as a hexose, right? Here you are going to get as a hexose, and in that hexose one of the structure is a glucose. From where that glucose we are going to get, because you know the structure of the glucose, I am sure. So these are the hexose. So from here you are going to get the compound hexose, right? And now look at here, while same thing you have to draw over here. This CHO, what you have to do? You have to write down those structures as it is. Here CH2, then OH. Now here 1, 2, 3. So here you write 1, 2 and 3, and one extra you have to put over here because you are going to add as a one of them. So this is a hydroxy group over here, OH and OH. All three hydroxy group on the right hand side. This and this you have to write over here. And now what you keep as a one thing is empty over there. Then CHO, then write this one, CH2OH. These three things as it is, 1, 2 and 3, one keep as empty. So all that hydroxy OH, OH, OH over here, hydrogen, hydrogen and the hydrogen. Right? Now here also you have to write down this one CHO, and then other thing remains as it is, CH2OH, 1, 2, 3 and 4 you have to keep over there because 4 chiral center is going to generate over there. In every step one of the chiral center is goes on increasing. Here what you are going to get over there, so here you are going to get CHO, then here look at here, OH, OH on the right hand side and one OH on the left hand side. Remaining you have to show by the hydrogen atom. Now here I am keeping as it is CHO, then here CH2OH. Look at this carefully. Again 1, 2, 3 and 4 is going to get as empty. Now look at over 1, 2, 3 over there. Sorry, what we are, yes, 1, 2, 2 hydrogen OH group on the right and OH, H and the H over here. And now let's see over here, and here again as a CHO, then here I am writing CH2OH, 1, 2, 3 and 1 4 extra addition, then CHO. Now I am writing this CH2OH, 1, 2, 3, 1 extra over there. Now here is again is a CHO, then CH2OH, 1, 2, 3 and 4 is there, and CHO. Then I am going to write this one CH2OH, 1, 2, 3 and 1 4 extra is there. Now only the structure. Now look at here, we are written this structure as it is. Now where I should put hydroxy group on the right hand side and left hand side is a hydrogen. Here now exactly opposite, HO here and hydrogen atom here. Now look at here, hydroxy group I am going to put on the right hand side, in this case on the left hand side. Right? So this is the structure, and now in this case whatever structures are there, OH on the right hand side, then H, then OH, right? These are there, then H, HO, then this is a H. Now where should I put hydroxy group on the right hand side? Here hydroxy group on the left hand side, hydrogen. Here hydroxy group on right hand side, here left hand side. Here left hand side, here is a hydrogen side, and rest of the thing you have to write down as it is. Here OH, H and OH, here H, HO, H. In this case also, now not from this, now here is a H and this OH, H, HO, and here also what is that? Here you should write as it is H, OH, then H, HO, and all are the D series. Why? Because if you see the lowest chiral center, the hydroxy group on the right hand side, and therefore they are designated as, in every case if you see over there you will find there are the D configuration. The naturally occurring carbohydrates are D configuration over here. Look at this one everywhere. And now from this 8 isomer, what is your job now? You tell me which one will be the D glucose. Look at here, D-glucose is obtained from the D-arabinose. This is the structure of D-glucose. Remember, this is the structure of D-glucose. This is the structure of D-glucose, and whereas this is the structure of D-mannose. This is the structure of D-mannose. This is the structure of D-mannose, and this is the structure of D. And the first, this is the structure of D-allose. I am writing because there is no space, so I am writing above one, D-allose, and this is the structure of D-ultrose. This is the structure of D-ultrose. Look at, these are the structure. And now if you look at gulose, this is the structure of D-gulose. D-gulose, and this is the structure of, what is that? Iodose. This is the structure of D-iodose. D-iodose. Iodose. And the next one, galactose. This is a D-galactose. Galactose. This is a D-galactose. And last one will be the D-talose. D-talose. Talose. So these are the structure of D-glucose and the D series. So in this way, we have seen the general trick to synthesize. So tomorrow we are going to start as a, what is that Kilone-Fischer synthesis, how it is synthesized that D-glucose, the method of preparation of the D-glucose, that we will see. Tomorrow's lecture, I think, I hope you understood how we are getting as this type of the carbohydrate, lengthening of that carbohydrates in a particular cases. So I think with this, let us stop today here. Have a nice day. Thank you.